Thank you for joining us again this morning for our webinar. This morning it is high-speed counting. So the video is roughly 21 minutes, give or take. And as usual, if you have any questions, put them into the questions panel at any point throughout the presentation, and we'll get to them at the end in a live Q&A. So let's get started.
Welcome to today's tutorial on high-speed counting. Let's get started. Let's take a look at our agenda for today. We're going to talk about some applications that require high-speed counting and the different ways you can use the functionality built into Horner products. We'll talk about common terms that we use with high-speed counting. We're going to cover the different modes that are supported by our products. At the end, we'll do a comparison between the different Horner product lines and what the high-speed counting capabilities are from series to series. And as always, we'll end with a Q&A session. Let's get started with high-speed counting. We'll start with some example applications. You may need to keep track of machine position. An encoder can be used with Quadrature so that we can get position information into the controller in real time. You may need to count products on a production line. If you're doing that, you'd be using Totalizer mode with a photo eye sensor. You may need to cut a product to length. You can use an encoder or a sensor to ensure you have the right length, alongside an automated cutting output which will cut the product to size. Or you may need to measure the flow rate of liquid for a process application. You can use a flow rate sensor that has a paddle wheel built into it. By monitoring and measuring frequency, you will know what the flow rate is. At Horner, we've been doing high-speed counting for years. It's provided a lot of power, flexibility, and performance. We utilize a special piece of silicon, a component called either an FPGA or CPLD, and this is a dedicated part that handles all the high-speed input and output requirements for the application. It doesn't require time-critical signals to be dependent on the logic scan in order to perform their function of counting an output. Those high-speed input signals are wired directly into the gate array chip. The high-speed output signals are also wired directly into the gate array chip. Using Cscape, we configure the mode of counting that we're going to be using. Those 4 high-speed inputs can be flexibly reconfigured depending on the application. You have a bank of assignable real-world I/O type registers that you can use for non-time critical functions. This approach of using dedicated silicon means very strong performance with high frequency supported and a lot of flexibility in the functionality of the machine. Now let's talk about some common terms that we'll be using to ensure you understand what we're talking about. Totalizing is a term for maintaining count. We often call counting totalizing. The accumulator is a special register where the current count is stored. We use that same term when we talk about timers and counters in logic, but in this case we're talking about a special accumulator, where the high-speed counter information is stored, where we can retrieve it and where we know that value is accurate, regardless of scan. These next 4 terms are functions. An external or internal disable signal will prevent the counter from counting when you don't want it to. The clear function sets the accumulator to 0 as long as it's active. The preload function does the same thing, except the value does not have to be 0. The latch function, sometimes called the strobe function, takes the current value of the accumulator and places it into a latch value register. Edge-sensitive signals and level-sensitive signals apply to the configuration of the 4 functions I previously mentioned. Edge-sensitive signals trigger when the signal changes from 0 to 1 or from 1 to 0. Level-sensitive signals trigger while the signal is currently at 1 or 0. Okay, now let's talk about all the different high-speed counter modes that we support in our Horner OCS product lines. I will quickly summarize the different modes we have now. We have a series of totalizing modes which we'll go through individually. We have frequency measurements, where we measure the frequency for a particular pulse train. We have pulse width measurement, where we measure the width of the on or the off pulse. We have period measurement, where we measure the entire on plus off cycle to report the period. And we have quadrature mode, which we use when we're interfacing with an incremental encoder position, whether that's linear or rotary position. Now let's talk about the totalizing options. One mode of totalizing is where you're counting time ticks from an internal clock using an accumulator. The other totalizing options are all about counting events. We may want to count up all of the time, we may want to count down all of the time, we may want to count up and down. So one input signal is going to cause our accumulator to increment, and another input signal is going to cause our accumulator to decrement. We have a variation on the up-down, and that is clocking direction, where we're going to count every time the first input is on. Whether we count up or down is going to be determined by the state of the second input. Let's look at examples, starting with event count. In this example, I'm configuring the high-speed inputs for this function to count the number of products in my machine. I've configured the real-world high-speed counter input number 1 to count up. If you look at the screenshot on the right of the Cscape configuration, you can see that I'm in Totalizer mode. The input for my account is external input number 1. I'm going to be counting when input 1 transitions from off to on. I've configured it so that I don't always want to count. I've allocated real-world input number 2 as an external signal that will disable the counter when it's high. At some point, it will clear the accumulator, but that's not a time-critical function, so I'm just assigning an internal real-world I/O bit, or a Q bit, as the clear function. I will turn that Q bit on in my logic to execute the clear. Then my accumulator will contain the product count. My clear function is not asserted in logic. Where is the accumulator assessed? There's a set of IQ, AI, and AQ registers that are assigned to the high-speed counter. Those can be moved around, but the defaults are shown in these tables. For my example, I need to look at the accumulator, and that's an AI 401 as a double integer, so it's a 32-bit accumulator. The clear function that I'm going to perform in logic is Q1603. So by turning that coil on, I will clear my counter. In the high-speed counter chapter in the user's manual for every product we sell, you will find all the details about the default memory map for the high-speed counter function. Let's move on to the next example. We're going to count the time ticks between two inputs in this next application. So how can we set this up? The diagram shows you what the signals look like. I've got two inputs. I've got a pulse that comes in on input number 1, another pulse that comes in on input number 2, and what I'm interested in is the elapsed time between the leading edge of both pulses. One way I can set that up is by utilizing Totalizer mode. You can see the snapshot from the high-speed counter configuration for the Totalizer mode. It's configured for internal and to count internal clock ticks at a 1 MHz rate. So by manipulating our clear function and our latch function, we can end up with the elapsed time in 1 microsecond increments in our last register and get the value that we're looking for. To review the configuration there, we start out by saying that our first real-world input, which is the first pulse, is going to clear the counter on its rising edge. We've configured the clear function for external input number 1 and as a rising edge type clear. What that means is that the accumulator will start from 0 when the clear is complete, and it will start counting 1 microsecond clock ticks. This will continue to occur until the second input turns on, because the second input is configured as a latch and as a rising edge. As soon as that second input goes high, then we will latch the value in the accumulator, which will be the number of 1 microsecond clock ticks since our first pulse went high. And then when we do a latch, we copy the current value of the accumulator into a latch register. It'll be frozen in time, while the accumulator will continue to increment with values beyond what we want to measure. The last value is the devil word register, right after the accumulator for each counter. I'm using an XL4 high-speed counter for these specific examples. Let's talk about frequency counting. Instead of selecting Totalizer as your type, you select frequency counter. Now you have 4 options for how often you want the OCS high-speed counting function to calculate frequency. You can calculate it every second, every 100 milliseconds, every 10 milliseconds, or every millisecond. The faster you recalculate, the lower your accuracy and narrower your frequency range will be. Select frequency and then select your update rate. In our example here, we have liquid flowing through a paddle-style flow meter. I've configured it very simply. Input number 1 is set for frequency mode and 1 second updates. I'm not configuring anything for disable latch. I'm just allowing the frequency to be updated in the accumulator once per second. In my logic, I'll be able to take that frequency and then, using a conversion factor based on the documentation for the flow meter, convert that frequency into a liquid flow. Now let's talk about accurately measuring the width of the pulse. You can measure the width of the pulse when it's high or when it's low. In my example, we're going to measure the width of the pulse when it's on, or high. We're wiring the signal to be measured as high-speed counter input 1. I've configured pulse width measurement for my type. My results are going to be in 1 microsecond counts, connected electrically to the external input number 1. As pulses come in, the accumulator will be displaying the width of the last pulse in 1 microsecond increments. The accumulator is continuously updated as new pulses come in. Let's talk about measuring the total period of a pulse. We're going to measure the entire on-off cycle of the signal. We set it for a period measurement. We start measuring the period from the rising edge. We could also start measuring the period from the falling edge or the trailing edge. As cycles come in, the accumulator is continuously updated. And as those cycles come in, the period is going to be reported by the accumulator in microseconds. Now let's talk about quadrature. Incremental encoders are the most common devices that use quadrature. With quadrature, an encoder typically has two outputs, an A pulse and a B pulse. Those pulses are configured so that they are 90 degrees out of phase. The A pulse is wired to input 1. By monitoring these two signals, the high-speed counter will count up when A is leading B, or input 1 is leading input 2. The counter will count down when the opposite is true. Most encoders are rotary. If it's moving clockwise, it's very possible that A is leading B and will count up. If it's moving counterclockwise, it's very possible that B is leading A and will be counting down. The counter is counting both the leading and the trailing edge of each pulse. So for an encoder that has a rating of 1,000 lines per revolution, we actually get 4,000 counts per revolution. In Cscape, under type quadrature, we can select whether we want to count down or count up when 1 is lagging 2. The A signal is connected to input 1, the B signal is connected to input 2. Some encoders have a marker signal, which you can use with the OCS if you choose. A marker post is a post that's on exactly once per revolution. In this example, I'm not using the marker. I'm going to use a clear function from an internal bit and assigned Q. I'm doing that because I'm probably going to clear the accumulator when I use a find home function or similar, and that is typically done at low speed. Over the next couple scans, I'm going to clear the accumulator, so when I start moving again, I'll start counting in the appropriate direction and have an appropriate value for position. The accumulator contains my current position and counts. When looking at where we can find the clear bit, we see the clear bit on Q1603. That information is in the high-speed counter chapter of the user's manual. We've reviewed the different modes that are available in the OCS high-speed counting functions. Now let's talk about some of the capabilities of individual product lines in terms of how they support high-speed counting. All of our Micro Series OCS products support high-speed counting. The MicroOCS series is the newest series of OCS products. They are entry-level products, but even though they're entry-level, they have very good high-speed counting capability. Our XL series OCS also does a very good job with high-speed counting. We also have an RCC 6512, a programmable high-speed counter coprocessor. It doesn't just count, it also provides a variety of advanced counting functions, and has a very flexible means of interfacing over a variety of networks, Ethernet, CAN, etc. It also has some built-in logic capability to do logic remotely. It's typically used with other OCS products. It doesn't need to be, but the amount of local logic is limited, which I'll talk about later. Let's start by looking at the MicroOCS series. This is a very cost-effective line. The max supported frequency is 500 kHz. Most entry-level products are around the 1 to 10K range. We can handle signals up to 500K. We can also handle up to 4 counters. It does not support all the totalization modes for totalizing. It primarily supports counting up, but also supports frequency counting, pulse measurement, period measurement, and can handle up to 2 quadrature encoders. It can handle up to 2 match outputs, which are real-world outputs that are wired directly to the FPGA. They can be controlled from the high-speed counter chip, so when a certain count or position is reached in the accumulator, you can automatically fire those outputs independent of scan, which is very powerful. It gives you programmable limit switch type functionality. There are 2 high-speed outputs that can support that mode. However, they strictly turn on based on accumulator value. Next, let's take a look at the 2 entry-level points to the XL series, the XLE and XLT with Ethernet. These products are updated versions of the classic XLE and XLT, with added built-in Ethernet capability, along with faster processors and upgraded high-speed counters. They support up to 500 kHz frequencies and up to 4 counters. Its mode support is very similar to the Micro series. It supports Totalizing count-up only, but it also supports frequency counting, pulse measurement, period measurement, quadrature errors, and match outputs for turning on an output based on position. Let's talk about our mainstream XL OCS series. These products have more powerful processors than the XLE and XLT, and are Linux-based. The XL series has very good frequency support, up to 1 MHz. Because the XL series FPGA chip was designed several years ago, it supports 2 highly functional counters. You can update the firmware by contacting our tech support group to get up to 4 counters, but they're not quite as capable. All the totalizing modes are supported: frequency counting, pulse measurement, period measurement, and quadrature. But if you're in 4 counter mode, there's no quadrature support. There's also match outputs, which can either turn on based on position or value in the accumulator, turn off, or toggle. The X5 has the same internals as the XL family. It looks like a micro from the standpoint of its packaging. However, its high-speed counting capabilities are aligned with XL series and not with the Micro series. Let's talk about digital filtering. Whenever you're counting pulses or transitions and you have a count error, which is capable of reading very fast signals, you have an opportunity for spurious signals that might just be noise to be counted. With digital filtering, you can eliminate the potential for spurious signals. In most high-speed counter applications, you have a certain frequency, period, or pulse width in mind when you set up the application. You can configure our digital filter and the high-speed counter function to accept all of the legitimate pulses and signals, but reject the pulses that don't belong. There are 2 settings with our filter. The first thing you set up is filter frequency on the setup dialog. I've set up my sampling frequency at 20 kHz. That means that on a 20 kHz rate, I'm going to be sampling each input of the high-speed counter to check its level. Then I configured how many consecutive samples have to match before I'll either pass my on or my off to the accumulator. So I've got all the calculations here. If I set up this digital filter at a sampling frequency of 20 kHz, then I need 4 consecutive samples before I pass the signal on. My sampling period is 50 microseconds. I need to have 4 consecutive samples to match, which means the minimum valid pulse I'm going to receive is 200 microseconds wide. Let's assume a 30% on, 50% off duty cycle. Then we have to take our 200 microsecond pulse width and double it to get a period of 400 microseconds. When we invert that to get frequency, we come up with 2.5 kHz. So I've configured this filter to filter out the high frequencies above 2.5 K. Alright, next we're going to talk about the RCC High-speed Co-Processor. We have taken some advanced high-speed counting hardware and wrapped it around a microprocessor that has logic capability. We've added flexible communications networking, including Ethernet and CAN, and we've provided logic capability so that you can program locally in ladder logic. We still have the FPGA with high-speed inputs and outputs wired to it. We have 12 physical digital inputs and 8 physical digital outputs that are wired to our gate array. We support maximum frequencies up to 500 kHz and up to 8 accumulators. We support all the totalizing modes: frequency counting, pulse measurement, period measurement, and quadrature. We support 4 quadrature channels, and you can mix and match between quadrature and totalizing. It is highly configurable. We have up to 8 match outputs, which are digital outputs that we can fire based on an accumulator value. We have a much more flexible input voltage than we have in our standard products. This product supports not only 12 and 24 volts, but it supports 5 volt levels as well as 0 volt levels. Instead of digital filtering, This product supports analog filtering. You can set up an analog filter at either 500 kHz, 50 kHz, or 5 kHz to filter spurious noise signals that you don't want. From a logic standpoint, this unit is programmable in ladder logic, but is slightly more limited than most of our products in terms of the amount of logic and variables that it supports. It supports up to 16K of ladder with a limited number of variables, about 1800 that are non-retentive and 256 that are retentive. We've got 2K non-retentive bit types available as well. From an Ethernet standpoint, it supports Modbus TCP as a master or a slave. It supports Ethernet IP as an I/O device. It also supports FTP file transfers and email. From a CAN standpoint, it supports our standard C-SCAN protocol, and you can communicate to other OCSs over C-SCAN. Here you can see what the high-speed counting capability of our products is. I've highlighted the areas where there's some differentiation. While the XL series has a very powerful high-speed counter built in to counter mode, it only supports a total of 2 counters. If you need 4 counters, you need to make a firmware change or update. The RCC 6512 can support a total of 8 counters. It has analog filtering instead of digital filtering, and it has 8 match outputs. It also supports up to 4 quadrature inputs. Thank you for attending today's tutorial. The Q&A session will begin shortly.
Okay, that was that. Let's see if we have any questions in there now. On the XL series, can we use Quadrature in 4 counter mode? Excuse me, no, only in 2 counter mode. And as you saw on the table there, we do support 2 quadratures in 2 counter mode. How can I get 4 counter mode? I don't see the option. I believe that came in just before that slide. You can contact tech support and we will send you out the file as well as the procedure for updating the 4 counter mode. There's no hassle there at all. The function register maps in the slides, where can I find those? You can find that in the user manual of your controller in the high-speed counter section. So that'll all be there with added detail as well. I don't see anything else there just now. I'll take you to the webinar page there again now and show you what's coming up in the coming weeks. Okay, you should hopefully be seeing my screen there now. Please raise a hand if you don't. So yeah, we've the next 4 weeks after this scheduled out. So we've language translations next week, and then we'll go into real-time clock functions, integrating stepper motors, and wiring of the MicroOCS controllers in the following weeks. It'll be the same time every week, same day, so Thursday, same time. We'd love it if you could join us again for those. And yeah, the registration links are here on the right as always. So they are available to register right now. So if you want to do it now and get it out of the way. Yeah, that's it for this morning. Thank you all for joining us again. And we hope to see you again. Thank you very much.